To see why we might consider using different coordinate systems, let's think about reflections. So let's suppose that we want to figure out how to reflect across the line y equals 2x. We can understand this operation geometrically as follows. First, take a point, xy, and draw a line through this point perpendicular to the line y equals 2x. Second, measure the distance from the intersection of these two lines to the point. And third, to find the reflection, you simply choose the point on the opposite side of the line y equals 2x, equidistant from the intersection. Graphically, this is very intuitive. So if we sort of tilt our heads a little bit to the right, then we could simplify this problem by realizing it as a reflection across a vertical line. So to do just that, we can perform a change of basis. And in fact, we can perform exactly the change of basis from our previous example. So if we use the vector u, which is e1 minus a half e2, and the vector v, which is e1 plus 2e2, then we can think about our blue line as being the v-axis. We can think about this orange line as the u-axis. So of course, we get a new coordinate system, and our reflection now, instead of being across the line y equals 2x, is simply a reflection across the vertical axis, which we already know how to handle. So now that we understand this geometrically, we can use this change of basis business to perform the actual algebra. So we have two bases, E, the standard basis, with the usual x and y coordinates, and B, our new basis. So if we want to convert from the coordinates corresponding to our new basis to our standard coordinate system, then we use the matrix, which we're going to call C, subscripted with a B, whose columns are U and V. Then, to convert in the other direction, from the standard basis to our new basis, we use the inverse of this matrix. So I've gone ahead and asked Sage to simply compute this matrix for us. Its columns are 4/5, 1/5, -2/5, 2/5. So in order to convert our original point, which had an x-coordinate and a y-coordinate, into our new uv coordinate system, we simply take this vector xy and multiply it by this second matrix. When we do this, we get the vector expressed in u and v coordinates, 4/5 x minus 2/5 y, and 1/5 x plus 2/5 y. Now, if we want to think about this in our new coordinate system, let's draw a quick picture. I have two axes, the horizontal axis, which corresponds to the vector u, and the vertical axis, which corresponds to the vector v. In u and v coordinates, the point that we started with can be expressed with u coordinate 4/5 x minus 2/5 y, and v coordinate 1/5 x plus 2/5 y. A horizontal line, which I'll draw in red, is a line whose v coordinate is equal to 1/5 x plus 2/5 y. And to get the reflection of our point across the line y equals 2x, which of course corresponds to reflecting our point across the vertical axis, is simply one in which we negate the first coordinate. So we note that we can encode this reflection across the v-axis as a matrix transformation given by the matrix R, whose entries are -1, 0 and 0, 1, which simply negates the first coordinate of a point. So we can think about starting from our point xy, then translating that into our new coordinate system as multiplying the vector xy by c sub b inverse, then multiplying the result of that by the matrix R. Now, at this stage, we have figured out how to reflect the point. However, this point is still written in terms of the coordinates u and v. If we want to write this transformation in terms of coordinates x and y, we simply need to convert back to our xy coordinates. This simply means multiplying the representation in uv coordinates by the matrix CB. When you do this, the result of this operation will be the vector with coordinates -3/5 x plus 4/5 y and 4/5 x plus 3/5 y. So in fact, we can think about this translation as a matrix transformation. And you can see from this vector on the right that our matrix, given by c sub b, multiplied by the reflection R, multiplied by CB inverse, is -3/5, 4/5, and 4/5, 3/5.